Alright, I thought I'd make a video for you for 3.1. Maybe it's a little bit shorter than the one that you're currently going to be watching. But this is another explanation of 3.1, Extrema on an interval. And just a quick thing on the homework, I should be page 169. 2 through 10, all 14 through 32 by 3, then you should end up at 32 and number 42. And you should read through 3.2. There's some videos up to if you want to watch. I will give notes on 3.2 on Friday. Okay. Alright, so we're going to be talking about extrema on an interval. And they've got a lot of talk about extrema, and I know that in the first video they did a very good job of describing what extrema were. So briefly, I'm just going to go and show you some things in the book here. So the definition of extrema on pages 164 and 165. The main thing you need to know, extrema are places where there are highest and lowest values. So extrema of a function, the extrema of a function are like the maximums and the minimums. But there are also other points. There are also points that where like there's sharp corners and asymptotes, and we'll get into those more later. But the main thing we're finding today are what we call extrema, maximums and minimums, and absolute maximums and minimums. And don't get hung up on the difference between absolute, relative, that kind of thing. The main thing you need to know is that a function has maximums and minimums at places like right here. There's a minimum. There's a whole bunch of minimums on this page. If we look over here, okay, we've got a function. This one has a maximum and a minimum. Okay. Now in this function here, if you were to extend this function, it basically just, it looks like this. Okay. So this is called a relative maximum. It's a maximum because it is a special point, and we'll see why in just a minute, why it's special. But it's not the absolute highest point in the whole function, because these points, any point here will always be higher. So any point up here will always be an absolute maximum, where this is a relative maximum. This is a relative minimum because all these points will be lower, but this is actually a critical number. This little point right here at 2, -4 is much more critical of a number than any of these points down here. So we've got this function here. This has a little max, a relative maximum here. This has a relative minimum, and this also one down here is a place where the derivative is not defined. There's no derivative there, but it is a minimum. And then we've got just other pictures. So the first thing we're going to look at, just in the example, is what is the derivative, value of the derivative at the relative extrema. So we've got a function here, and we have its graph, and here is its relative extrema. How do I know? Because it is a place where it is the lowest point on the graph. So we just want to explore what is the value of the derivative at a relative extrema. So in this case, how would I do that? I would just take the derivative. So find f prime of x. I'm just going to use the quotient rule. So the quotient rule gives me, okay, take the bottom, x squared plus 4, times the derivative of the top, 2x, minus the top, x squared, times the derivative of the bottom, 2x, all over the bottom squared. And I'm just going to simplify that a little bit. So f prime of x is, let's see, distribute the 2x, I get 2x cubed plus 8x minus 2x cubed again, all over x squared plus 4 quantity squared. And so there's my first derivative. I can combine a couple like terms on the top, and if I do that, my f prime of x is 8x, because the 2x and negative 2x cubed cancel over this. So now my point is at 0, 0, so if I plug 0, 0 in, basically you're just putting the x value in. Okay, if I plug 0 in for the x, I get 0 over 16, which is 0. So the value of the derivative right here at this point is 0, and I want you to make a very big connection right now. The value of the derivative at relative extrema, if it's a minimum, is going to be 0, because its derivative is the slope of the tangent line. If I draw the tangent line to the curve right here, it's a horizontal line. Its slope is 0. If it were a maximum, okay, if it were up here, the value of the derivative at that point would be 0. All right, so now let's take a look at the next one. Same exact thing. Let's find the value of the derivative at this extrema. We're going to have a slightly different outcome here. So I take the derivative, f prime of x. Okay, you don't know that you're going to get a different outcome, so just take the derivative. So you multiply, use the chain rule. So the outer function is the 2/3 power. The inside is x plus 2. So I multiply by 2/3, leave the x plus 2, subtract 1 from the power. I get negative 1/3 times the derivative of x plus 2, which is 1. So f prime of x, on the top I have 2, on the bottom I have 3, and then x plus 2 to the 1/3 power. So that's the cube root. I want to find the value of the derivative at that point, at negative 2 comma 0. What is the value of the derivative there? Put negative 2 in for x. So f prime of negative 2. 2 over 3 times negative 2 plus 2 to the 1/3 power. That gives me no solution. No solution. Undefined. Why? I get 0 on the bottom. I get 2 over 0. That's what I get. Undefined. Okay, well, isn't this a minimum? Didn't you just say, Mrs. Kern, that a minimum value has a slope of 0 or a maximum? This is different. This is a minimum, but it's also a sharp corner. And we learned a while ago that at a sharp corner, a derivative does not exist. So, key things. The value of a derivative at an extrema, a critical point, which we'll learn about in a minute. A maximum, a minimum, they're all interchangeable, is either going to be 0 or undefined. 0 slope, no slope. Okay, that's key. All right, so now we've got definitions here, and these are all in your book. Definition of a critical number, this is very important. A critical number is a max, a min, a place where there's no derivative. Okay, a maximum, a minimum, a place where there's no derivative. That's a critical number. It's critical to the picture of the graph. Okay, so let f be defined at c. So c is the critical number. Okay, c is the critical number. It has to be defined there. If the derivative is 0, if f prime of c is 0, or if f is not differentiable at c, then c is a critical number of f. So we go back to the last problem we had. We've got here's a function. The value of the derivative here was 0, so it is a critical number. The value of the derivative here is undefined, so this is a critical number, critical points on the graph. Why? They are points that are imperative to the picture of the graph. Without, that point, that's where it changes. That's where it changes direction. Critical points are direction changes. All right, so theorem 3.2. Relative extrema occur only at critical numbers. Okay, only at critical numbers is very important, because if you could find them somewhere else, then calculus wouldn't work. You find the derivative, you set it equal to 0 and solve it, and that gives you your critical numbers. That's the only place they're going to happen. All right, so now we have guidelines. Well, I'll read the definition. If f has a relative minimum or relative maximum at x equals c, then c is a critical number of f. It's like these are saying things backwards, okay? If it's defined at c, if the derivative is 0, then it's a critical number. If it has a max or min, then it is a critical number. So it's kind of just restating it. It's important that you know that critical numbers of functions happen where the derivative is 0 and undefined. So here are guidelines for finding extrema on a closed interval. The first thing you're going to do is find critical numbers of f in AB. Okay, the way you do that, this is what we just kind of went over. You find the derivative, set it equal to 0, and solve it. Those will give you your max-min critical numbers. Those are going to give you your maximum and minimum critical numbers. Then you have to look at both your function and your derivative and say, where is my function maybe not defined, because that will be a critical number, and where's my derivative not defined, because those will be critical numbers. You don't always have both. Most of the time you're just going to be finding the derivative, set it equal to 0, but you have to look at your function and say, where is my derivative undefined, because that is also a critical number. So then you're going to evaluate f at each critical number that you got from here. Then you're going to evaluate it at the end points. Okay, we're finding the extrema on a closed interval, so just a certain little section of a function. And then the smallest number from all the work you did is the minimum, the smallest y value, and the biggest y value is the maximum. So we're going to look at some examples now on how to do this. So I'll only make one video, so whatever I get through, I get through. I think I've got like 7 or 6 examples, so these don't take long. So find the absolute extrema on the interval. So step 1, I'm going to find the derivative of this, f prime of x, which is negative 2x plus 3, and I'm going to set it equal to 0, and I'm going to solve it. Okay, so Well, I'm just going to subtract 3 divided by 2, so x equals, subtract 3 divided by negative 2 gives me 3/2. So that means that this function right here has a critical number at 3/2. Okay, that is where the derivative is 0. There's a critical number. So that's the one I got from step 1. Now I have to look at this function and say, is there any place that this function is undefined? Well, no, because it's a polynomial. The derivative is always defined. So this is the only possible critical number. Only critical number in the interval from 0 to 3. Okay, so we're looking at in this interval from 0 to 3. So this is the only critical number in that interval. Okay, so now it says in the steps, I take that and I put it into the function. So if I put 3/2 into the function, just do it on your calculator, negative, begin parentheses 1.5 squared, and then plus 3 times 1.5, and you get 2.25. So the y value that goes with that is 2.25. Okay, now we need to look at the end. So this is the critical number in here that I found by setting the derivative equal to 0. Now I need to find what's the y value that goes with 0 and what's the y value that goes with 3. So basically I'm going to have 3 ordered pairs. I'm going to have 3/2, comma 2.25. There's my critical point within this interval. Then I put 0 in, I get 0. If I put 3 in, I also get 0. So the maximum is 2.3. The maximum is at x equals 3/2, and it's 2.25 is the maximum value. The maximum value is at the x value, but the maximum value is 2.25. You could just say the max is 2.25. The minimum value occurs at x equals 0 and x equals 3, and it is 0. So if you look at a graph of this, it's a parabola that opens down. Okay? The maximum is the vertex or the highest point. All right, so now let's take a look at number 2. Find the absolute extrema on the interval. So the first thing I'm going to do is take the derivative, so f prime of x, using the quotient rule. Take the bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. I'm going to distribute and combine like terms on the top. 2x cubed plus 6x minus 2x cubed. The 2x cubes cancel. So I distribute it here. I combine these. So now I've got 6x over x squared plus 3 squared, and I'm going to now set that equal to 0. When I set that equal to 0, I'm going to multiply both sides by the bottom. And a nice thing happens. It cancels here, and that side is still 0. So then my critical numbers are, my critical number within the interval is x equals 0. My critical number endpoints are x equals -1 and x equals 1 from up here. I'm just going to plug those in to get the y values into the original function. Plug into original. Now, I skipped a step because I might have other critical points where the derivative is undefined. So here's my derivative that I had, 6 of x over x squared plus 3 quantity squared. Are there any values that I can put in that would make that undefined? In other words, is there anything that would make the bottom 0? And since that's a plus, it's not going to work. So the derivative is always defined. So these are the only 3 possible critical numbers. So now I just put 0 and -1 and 1 back into the original function. So when I put 0 in, I get 0. When I put -1 in, I get 1 over 4, 1/4. When I put +1 in, I get 1/4. So these two would be considered maximums, and this would be the minimum. It's the y value that determines the least and the greatest. The y value is what you look at. All right, I guess I am going to do one more video. I'll do the other 3 examples on the next video. Sorry.